Stokes' theorem is another formulation of the fundamental theorem of calculus. In this case, we're going to evaluate integrals over a surface by considering what happens on the boundary of that surface. So we will have an oriented surface, which is a piecewise smooth surface. I'll call that surface S. And it's together with a chosen unit normal vector field n that is continuous on each smooth piece of S. So for every point on S, we're going to have a unit normal vector, and I'll call that unit normal n. And then the positive orientation for the boundary C of an oriented surface S, as pictured here. So I'm going to have a boundary of this open surface, and that surface is going to be bounded by a curve C. I'm going to orient it in this direction. And the positive orientation corresponds to the unit tangent vectors. So I'm going to draw a unit tangent vector T, such that T cross N always points out of the surface S. So if you look at T and N in this case, you can use the right-hand rule, and you can see that that's always going to point out of the surface S. So what I've drawn here is going to be a positively oriented surface. And this is the picture that you should use when we're looking at Stokes' theorem. So Stokes' theorem says, let S be an oriented, bounded, and piecewise smooth surface in space with a positively oriented boundary C and a unit normal vector field N. So that's the picture that you see there. And we're going to suppose that R of T is a positively oriented parameterization of C. If the vector field F is continuously differentiable in a space region containing S, then the line integral of f dot dr around C is equal to the double integral of the curl of f dot n ds. So why is this like the fundamental theorem of calculus? Well, what is the fundamental theorem of calculus saying here then? What we're saying is that a surface integral, and it's a very specific surface integral, a surface integral of the curl of f and curl of f is a specific kind of derivative of f. So this is a derivative. Okay. And it can be evaluated on the boundary. Okay, a closed curve C. Whenever we're looking at the fundamental theorem of calculus, we're looking at the integral of a derivative can be evaluated by considering the function on the boundary. And so here we have a very specific derivative that we're integrating. That's the curl of f. And we're going to be able to evaluate that by looking at f on the boundary. Specifically, we're going to integrate f dot dr. Well, why would Stokes' theorem be true? I'm not going to present a full proof, but what I will do is I will look at Stokes' theorem in two dimensions. So if we looked at this as being in two dimensions, then my surface would be a region enclosed by a curve C. So I could draw a curve C, like this. Okay, give it that orientation. And then S would be the surface, the area enclosed by C. This is a two-dimensional surface, so it's just an area enclosed by C. Well, in this case, my unit vector n is just going to be k hat. Okay, so it's going to be 0, 0, 1. Well, if I look at a double integral of the curl of f, okay, dotted with k ds, then what I'll end up doing is integrating over that area S, and when I do the dot product, okay, I'm going to consider just the third component of the curl. Okay, well, the third component of the curl is dq dx minus dp dy. Here we're thinking about f as being p, q, r. Okay, so I'm going to integrate that dA, where a is like dx, or dA is like dx dy. And that double integral over that area looks familiar. In fact, that's what you usually see in the right-hand side of Green's theorem. And so that can be rewritten as the line integral of f dot dr. So that tells us that Stokes' theorem is really a generalization of Green's theorem, where instead of my surface just being the area enclosed by C, now my surface is going to be a general surface whose boundary is C. And so I won't prove for you in this video Stokes' theorem, okay, but the ideas are going to be similar to how we proved Green's theorem. Okay, so both Stokes and Green's theorems are special cases of like the fundamental theorem of calculus. Here we're going to evaluate this integral of a derivative, okay, by looking at the boundary. Now you may ask yourself, well, when do these kinds of integrals even pop up? Okay, well, it turns out that these integrals are used to calculate what is called circulation. Okay, so circulation for a vector field is going to be the measure of the tendency of a fluid defined by that vector field to move around the curve C. Okay, so here what we're measuring with this integral is circulation. That's a measure of the tendency of a fluid to move around C. In this case, then, if I have my boundary C, okay, so let's imagine that this is my boundary C. Then what I'm going to do is I'm going to sum up a bunch of curls of my vector field F. So I'm going to have a bunch of curls that I'm summing up using that surface integral. So here I am summing up a bunch of curls. And then the idea of Stokes' theorem is that the sum, so Stokes' theorem is saying that the sum of the tiny loops is circulation from the larger loop. Okay, so Stokes' theorem is adding up all of these curls, and then the sum of the circulation from the tiny loops gives you the circulation of the larger loop. So this is essentially going to be Stokes' theorem, and we're going to apply this to two examples. So we're going to begin with the first example that says, let C be the ellipse in which the plane z equals y plus 3 intersects the cylinder x squared plus y squared equals 1. We're going to orient the ellipse counterclockwise as viewed from above, and let F, my vector field, be 3z, 5x, and minus 2y. And our goal is going to be to evaluate the line integral f dot dr. So we're interested in the line integral of f dot dr. Okay, so we're going to orient our curve this way. And this would actually be a very difficult integral to compute because C is an ellipse, and that ellipse is the intersection of this plane that I've drawn, z equals y plus 3, and then the cylinder x squared plus y squared equals 1. It's going to be very hard for me to parameterize that ellipse. So instead, what I'm going to do is I'm going to do a surface integral. So I'm going to apply Stokes' theorem, which says that this is going to be equal to the surface integral of the curl of f dot n ds. So the first thing that I need to do is then compute the curl. So the curl of f, okay, that's going to be the cross product of the del operator ddx, ddy, ddz, okay, and f, which is going to be, in this case, 3z, 5x, minus 2y. Okay, so if I want to compute that curl, okay, I'm going to get I'm going to have the y derivative of negative 2y, which is negative 2, and then minus the z derivative of 5x, which is 0, minus j, times the x derivative of negative 2y, which is 0, minus the z derivative of 3z, which is 3, and then finally plus k times the x derivative of 5x, which is 5, minus the y derivative of 3z, which is 0. Okay, so del cross f is going to be negative 2, 3, 5. Okay, so that gives me part of it. Now I'm going to need my normal vector. Okay, so I'm going to draw a normal vector to this surface. Okay, so this is going to be my normal vector, the surface n. And n, right, we can rewrite, or we can express this as just negative the derivative of z with respect to x, negative the derivative of z with respect to y, and then 1. Okay, so here I'm going to be taking the derivative of this function z with respect to x, which is going to be 0, and then negative the derivative of z with respect to y is going to be negative 1, and then 1. So that's my normal vector. So that tells me that the curl of f dot n in this case is going to be, I'm going to do the dot product, so I'm going to get negative 2 times 0 plus 3 times negative 1 plus 5 times 1. And that's going to give me 2. Okay, well then this surface integral is not going to be very difficult to do at all because I'm going to be integrating a constant 2. So here, when I want to find the surface integral of del cross f, okay, dot n ds, that's in fact going to be the double integral of the function 2 over just x squared plus y squared less than or equal to 1, because that's going to be my domain, the unit vector there. Okay, so I'm integrating over this domain here. And I'm going to integrate that dA. Well, 2 is just a constant, so that'll be 2, okay, times the area of the unit circle, which is pi times 1 squared, or pi. Okay, so that was a very simple integral to do once I applied Stokes' theorem. Much simpler than if I had tried to parameterize the curve. Okay, now let's see if we can apply Stokes' theorem, but now in the other direction, where we want to compute the surface integral, and we're going to look at instead the line integral. So here, my vector field f is going to be negative yz, xz, and xy. And S is going to be part of the parabolic surface that lies below the plane z equals 4, and whose orientation is given by the upper unit normal vector. Okay, so here, my surface S is going to be that surface that's part of the paraboloid. And what I want to do is I want to evaluate this surface integral by instead considering the line integral of f dot dr. So what I need to do is I need to parameterize, okay, this boundary curve. Okay, so I'm going to indicate here the boundary curve, and then I want to parameterize it. So I'm going to parameterize it by r of t. Okay, and so this is a circle. It's a circle of radius 2 because I'm looking at the intersection of z equals 4 and z equals x squared plus y squared. Okay, so this is a circle of radius 2. Okay, I can parameterize that by 2 cosine t, 2 sine t, okay? But z in this case is 4 because I'm not sitting in the xy plane. I'm in fact sitting with a circle of height 4, okay? R prime of t is going to be, in this case, negative 2 sine t, 2 cosine t, and then 0. And so when I compute, say, f of r of t, well, I'm going to do negative yz. So that's going to be negative, y is 2 sine t, and then z is 4, so negative 8 sine t. Okay. And then xz, so that's 2 cosine t times 4, so that's 8 cosine t. And then xy, which is 4 cosine t sine t. So that's f of r of t. Okay, so now what I want to do is I want to do f of r of t dot r prime of t so that I can do that line integral. And so in this case, when I dot f of r of t with r prime of t, I'm going to get 16 sine squared t plus 16 cosine squared t, and then plus 0. So sine squared plus cosine squared in this case is 1, so I get 16. So here I'm going to do curve integral of f dot dr. Okay, that's going to be an integral for my parameterization. T is between 0 and 2 pi. So I'm going to integrate from 0 to 2 pi. Oh, and just the constant, C, 16. That was kind of nice. Okay. So 16 times 2 pi gives me 32 pi. Okay, and so in both of these cases, I applied Stokes' theorem in the direction that would make the integral much easier to do.